had to cut out there real quick. Going to pick up where I left off. I believe number 23 is where I am. So 23, interesting problem. It says find a unit vector that is orthogonal to I hat plus j hat and I hat plus k hat. So I need to come up with a vector, three-dimensional vector. I'll call it u, which will be labeled u1, u2, u3, the components. I need this vector to be orthogonal to this and to this. So let's call this vector v, this vector w, and let's figure out what those are. V is I hat plus j hat, which means that it's just 1, 1, 0. And then w is I hat plus k hat, which is just the vector 1, 0, 1. So I'm trying to figure out if I can find a vector called u that is a unit vector that is orthogonal to both of those. So let me start with the orthogonality. I need that u dot v is 0. Okay, that's what I need. So I need that when I dot these two together, I get 0. So if I dot this with this, I just get u1 plus u2 plus 0, because the last component is 0. That equals 0. So that means that u1, if I move things around here, must equal negative u2. All right, I also need that u dotted with w must be 0. So when I dot this with this, I get u1 plus 0 plus u3 must be 0. And solving for u1 again, I get u1 must equal negative u3. All right, so here's what I have so far. I have that in order for this to work, my u1 must be equal to negative u2, but it also must be equal to negative u3. So these two have to be exactly the same, and this has to be different in sign. So if I go back to my u, I'm going to say, okay, u1 is just going to be some number, right? And then u2 will be the opposite of that number. Okay, so just imagine moving the negative to the other side. u2 would be negative u1. And then over here, ignore this, move the negative to the other side. u3 must be negative u1 also. So far, that's what I'm going to need for the orthogonality to work out, for the dot products to be 0. But then I also need that this be a unit vector. So I want also the magnitude of u to be equal to 1. And the magnitude of u will be this squared plus this squared plus this squared. Since they're all u1s, and I'm squaring so the negative doesn't matter, I'm going to get u1 squared plus u1 squared plus u1 squared must be 1, which means that the square root of 3u1 squared must be equal to 1. Just add them together. And this means root 3 times root u1 squared must be 1. Right? And if I go and say then this right here means that the absolute value of u1 must be equal to, I just divide by root 3, 1 over root 3. So I could have this. I could have u1 be equal to positive 1 over root 3, or I could have u1 be equal to negative 1 over root 3. In either case, I should get a magnitude of this vector to be 1. So I think I'm ready. I'm ready to write down what u should be. let's first start off and say u is equal to, let's let u1 be 1 over root 3. And then the u2 should be the opposite of that, the negative, and the u3 should be the same as the second component. So that's one potential answer. Or you could have done negative 1 over root 3 and then change the sign positive and positive. And I'll leave it for you to check yourself. But if you take this and you dot it with this and dot it with this, you should get 0, and the magnitude of this vector is 1. Same thing here. If you dot this with this and then dot it with this, both of those should give you 0, and the magnitude of this vector is 1 also. So kind of an interesting problem there. All right, that was 23. 24. Find 2 unit vectors. So I want to find 2 unit vectors that make an angle of 60 degrees with the vector v is 3, 4. Now this is 2-dimensional, so I should be able to draw this. So here's the vector 3, 4. That's the vector v. I'm trying to come up with 2 vectors that form an angle of 60 degrees with this. So there should be another one, 60 degrees this way, and another one 60 degrees this way. Find those 2 vectors and make sure that they're unit vectors. So let's start out by talking about what one of these vectors would look like. So I'll call it u. So I'm thinking u somewhere over here, okay, u. But it's a unit vector, so it's probably not that long. It's probably going to need to be somewhere down in here like this. I need to come up with that. Well, let's just call it u1, u2. And what are some things we know about this? Well, the angle has to be 60 degrees between these. So I know that u dotted with v must equal magnitude of u times magnitude of v cosine of 60 degrees. I know that much. If I dot these 2 vectors together, I get 3u1 plus 4u2 must equal the magnitude of u. Well, I want this to be a unit vector, so I know that that length is going to have to be 1. And then v, the magnitude of this, if I do my little square root, square each one, I should get 5. And then cosine of 60 degrees is 1/2. So that tells me that, so far, trying to find my u, I know that 3u1 plus 4u2 must equal 5/2. All right? It's multiplying out the right side. And the other condition I had here that I haven't looked at was that u1, magnitude of u had to be 1, right? So let's go ahead and let's rewrite this and let's find its magnitude. The magnitude of u, do it right here. The magnitude of u is the square root of u1 squared plus u2 squared. That needs to be equal to 1. See, I have an equation, though, that contains u1 and u2, so I can solve this equation for, let's solve it for u2. We'll replace that in here, and then we'll have an equation with just u1 in it, and I should be able to solve it. So solve this for u2. You get 4u2 equals negative 3u1 plus 5/2. Which means that u2 is equal to negative 3/4 u1 divided by 4 plus 5/8. All right. So coming here, I'm going to rewrite this equation right here. I need this to be true. I know what u2 is. I'm going to leave u1 as u1. So this becomes square root of u1 squared plus, now I'm going to have this in here, negative 3/4 u1 plus 5/8 squared. That must equal 1. And I'm going to continue to work that problem right here. So this is a quadratic, well, it's a radical equation, but it has u1 is squared here, and u1 I'm going to wind up squaring. I need to actually expand that out. So let me go ahead and do that over here. What's negative 3/4 u1 plus 5/8 times itself? Negative 3/4 u1 plus 5/8. So here to here, you get 9/16 u1 squared. Let's see, here to here, what do we get? Negative, it's going to be a negative number, negative 15 over 32 u1. And then when I do the middle one, I get the same exact thing, negative 15 over 32 u1. And then the last multiplication plus 25 over 64. And then I can put these two together. That's negative 30 over 32 u1, which is, reduce everything out, 15/16 u1, negative. Okay, so coming back there, I think I can erase this now. We have that the square root of u1 squared plus this squared, which we just turned out to be 9/16 u1 squared minus 15/16 u1 plus 25/64 all under the root, that must equal 1. And I can start putting this stuff together. Well, let's square both sides. We square both sides and the root goes away. 1 squared is still 1. So now put these two together, get a common denominator. You should get 25/16 u1 squared. So I just combine those two. And then minus 15/16 u1 plus 25/64 equals 1. And I'll subtract 1 from both sides here. So if I subtract 1, what will happen here is I'll get minus 1 equals 0. And then I can rewrite 1 as 64 over 64. That way I can put those together. If you take 25 away from, oh, I'm sorry, if you take 25 and subtract 64, what do you get there? 40, can't do my simple math again. 29? So 25 over 16 u1 squared minus 15/16 u1 minus 29/64 equals 0. All right. Okay, so now this is a quadratic equation, so you could solve it. There's two solutions. I'm going to, before I go to quadratic formula, I'm going to just clear the fractions. So I'm going to multiply everything by 64. So when I multiply this by 64, this by 64, this by 64, that doesn't matter. We should get, so 64 divided by 16 is 4, right? It goes in there 4 times. Then times 25, so you get 100 u1 squared. Again, 16 goes to 64 4 times. 4 times 15 is 60, so minus 60 u1. And then over here, the 64's cancel, so minus 29 equals 0. And you know what? Oh my gosh. Okay, sorry, 39. Oops. See, simple arithmetic. 39, look, 64, take away 25, right here, borrow 5, 3, 9. I know, okay, this Cal 3, I should know how to do that, but my brain just doesn't like to work on basic arithmetic anymore. I'm not sure why it doesn't like it, but it doesn't. So this minus this should have been negative 39, not 29. That's going to change that. 39. Bah. All right, so you use your quadratic formula. And I'll just tell you what we get for the answers here. You get U1 after you simplify is equal to 3 plus or minus 4 root 3 all over 10, which is approximately, well, there's two different answers here, so I'll give you both answers. One answer is, if you convert it to a decimal, 0.9928. And if you convert the other one to a decimal using subtraction, negative 0.3928. So that's what your U should be, your U1 should be. And remember, we had an equation for U2. We had solved for U2 a while back. And so here's what we've got. U should be equal to the vector 0.9928, and then you have to go compute what U2 is. Go back and look at our equation for U2, plug this in for U1, and then when you do that, you should get negative 0.1196. And then if you do the other option, would be to let my U1 be negative 0.3928, and then if you go solve that one for U2, you should get 0.9196. Okay, so let's take a look at those. 0.9, this one right here, 0.9928 is here, and then down 0.1, so it's really close, like right in there, just down a little bit. That vector right there should be a unit vector and have an angle of 60 degrees. This one, here's negative 1, negative 0.39, so about right there. Go up about 0.91, somewhere in here. This vector should have unit length and should also form 60-degree angle right there. So that's it. That's how you work that one. Sorry about that 39. You're probably watching the video going, duh, should have been 39. Okay. Where are we? 25. So for 25, it gives you two lines, two equations of two lines here. 2x minus y equals 3, and 3x plus y equals 7. And it's asking us to find the acute angle between these lines. So these are two-dimensional lines, so I'm gonna graph them for us. If we take this equation right here, we solve for y, we get y is 2x minus 3. So that's what this becomes. This one we solve for y, we get y equals negative 3x plus 7. That'll make it easy for me to graph. This first one, I start negative 3. And then from there, I go use the slope 2 over 1. So up 2 to the right 1. And then I could do it again. I could go up 2 to the right 1. And I've got some points there. I don't have a straight edge in here. I used to have a ruler in here. Close enough. So that's one line. The other line, I start at 7. 3, 4, 5, 6, 7, right? And from that point, I use the slope negative 3 over 1, so that's down 3, 1, 2, 3 to the right 1. and then down 3, 1, 2, 3 to the right 1. Oh, they actually hit right there. So, like this. And what we're trying to do is we're trying to find the acute angle between these two lines. So the smallest angle between these two lines, which would be like this angle. We want to know what that is. Well, what we could do is we could just use as a reference this point and then start by trying to figure out, like, what is this vector right here? Or what is a vector that would point in the same direction as this one? Well, that corresponds to the slope of the line, right? The slope of the line is 2, which is 2 over 1. So if I look at this as a vector, I could say, let me call that vector u. It's going to be equivalent to the vector, or the vector 2, 1, right? Sorry, got that backwards. 1, 2. Slope is 2. So 1, 2. So to the right 1, up 2, right, would be running parallel to this line. And then let me do the same thing. Since this is a negative slope, I'm going to have to look at the vector that goes like this, okay? And the slope of that one is negative 3. So a vector that would be parallel running in the same direction would be the vector, let's see, we go to the right 1 down 3, so right 1 down 3. So if I can find the angle between those two vectors, it would be this angle. I know that, all the way from here around is 180. So if I just take 180, subtract this angle, that would give me this one. So let's find the angle between those two vectors. So I'm actually going to be finding right now this angle, which is theta. And what I know is that theta is equal to cosine inverse of the dot product of these two vectors. So that's 1 minus 6, so negative 5, over the length of this vector, which is the square root of 5, and the length of this vector, which is the square root of 10. And then I get on my calculator and compute that. So let me just take a look here. What number was this? 25? Yeah, that's good. And then if you do this on your calculator, you'll get theta is 135 degrees. But that's theta. We want this one, beta. We know that theta plus beta is 180. So we know beta plus theta is 180. That means beta plus 135 is 180. So that means beta is what? 45 degrees. So that's the acute angle. The smallest angle between those two lines. Now 26 works pretty much the same way. All right, so what else do we have on our list here? 31. Find the scalar and vector projections of B onto A. So for 31, they give you a vector, vector A. Let's see how much time, I only have 9 minutes. 3, 6, negative 2. The vector B, which is 1, 2, 3. And they want to find the scalar and vector projections. So we have two formulas here. The scalar projection, and they want B onto A. All right. So the scalar projection is equal to what we call the component of the vector B onto the vector A, which I gave in class is just A dot B over magnitude A. And then the projection we'll do afterward. Okay, so the vector projection. So we need to dot these two. So let's dot them. You get 3 plus 12 minus 6 over the magnitude of A, which is the square root of all the components squared. So 9 plus 36 plus 4. So you have on top 9, on the bottom, what's that, 45, 49, square root of 49 is 7. So 9/7. This is for 31. 9/7. All right, and that's it. And then let's do the vector projection. So the vector projection is going to be equal to, we call it the projection B onto A. So we have a formula for this, very similar to the last formula. It's A dot B over magnitude of A, very similar, but then squared and then dotted with the vector A. So a lot of this we already have. We have A dot B, which we knew was 9. The magnitude of A was 7, but we square it, so 49. And then dot that, times, sorry, I said dot, damn it, scalar multiple. We multiply that times the vector A, which is 3, 6, negative 2. And so just distribute through, and you're there. 27/49, 54/49, negative 18/49. Okay. So remember, this is a vector, that's a number. So when you take a vector B and you project it onto a vector A, which is what we just did, you're dropping a perpendicular down, you're coming up with this vector right here. The length of this vector is 9/7. The actual coordinates or components of the vector itself is this 27/49, 54/49, and negative 18/49. So that vector is the actual red vector. That number is the length of it. All right, 31, what else? 35. All right, so 35 is a little bit weird. They give you a vector. It says if A is equal to the vector 3, 0, negative 1, find B, find the vector B such that this is true. So that means the scalar projection is 2. So the length of it is 2. So we've got some vector that's given to us right here. We need to find a vector that when we project it onto this, the length of it is 2. That's what this is saying. So let's set up the left side of this, right? This is A dot B over magnitude of A. We need that to be equal to 2. So that's what we know. Now B, we don't know what it is. We have to find it. So let's call it B1, B2, B3. And let's talk about what A dot B would be. So if I dot that with that, I would get, let's see, 3B1, and B2 times 0 is gone, so minus B3. that's the dot product on top, over the magnitude of A. The magnitude of A is the square root of, we've got to just do the square of those components. So 9, 0 doesn't matter, plus 1. We need that to be equal to 2. And then 3b1 minus b3 must equal, this is root 10. And just multiply both sides by root 10. So 2 root 10. That's all. I mean, right now we have a lot of freedom. We need to find a vector that satisfies this, but we have one equation and two unknowns, so that means there's an infinite number of solutions. So we know what they need to look like though, right? Let me see. I have my vector B so far. B1 can be whatever I want. B2 doesn't look like it matters, because when I dot it with A, remember A was this? 3, 0, negative 1. When I dot these two together, that times 0 is not going to matter. So B2 is free to be whatever I want. And then B3, I could solve this for B3. So I could get like 3B1 minus 2 root 10. That's what you would get if you solve this for B3. So if I pick a vector that looks like that, it should satisfy everything that we want. So let's just pick some values. Let's let B1 be equal to 1. You know what? We'll be clever here. Let's let B1 be root 10. Because if I do that, then it's going to be easy to calculate. Let's let B2 be 0. So what would B look like then? B would be root 10, 0. And then 3 root 10 minus 2 root 10 is just root 10. And so I'm claiming that this, when you take the projection of that, the scalar projection of that onto A, you get 2. So let me check it. What is the component of B onto A? And is it 2, right? So let's do this computation, right? A dot B over magnitude of A. All right, and is that equal to 2? So A dot B. So we do 3 root 10, 3 times root 10. So we get 3 root 10. And then plus 0 times 0 doesn't matter. Then negative 1 times root 10 is negative root 10, so minus root 10. Over the length of A, but we did that earlier, that was root 10. Question is that equal to 2? Well, 3 root 10 minus root 10 is 2 root 10 over root 10. Is that equal to 2? Root 10's cancel, check. So it works. So there's an infinite number of answers I could have here. I mean, I could have changed this B2 to a 1, it would have worked. I could have changed the B1 to 5 and then worked through and figure out what this is. So infinite number of answers. This is one specific answer. Okay, 36, last problem. Suppose A and B are non-zero vectors. Under what circumstances is component of B onto A equal component of A onto B? So for 36, I think I'll do part A. I'll leave you to do part B. So given two vectors, A doesn't tell you if they're in two-dimensional or three-dimensional space. It's saying when is the component of B onto A equal to the component of A onto B. So when is that true? Well, let's just write down the definitions here. This right here means A dot B over magnitude of A. When is that equal to? This one means B dot A over magnitude of B. Well, what we know right now is that A dot B equals B dot A. So it doesn't matter, dot products are commutative. So the numerators are equal. So I can basically divide through, right? I can divide through or multiply through by 1 over A dot B. And now I'm kind of assuming something here. Right now I'm assuming that the dot product's not 0, or else I can't do this, right? So if A dot B is not 0, right, then I can cancel them out and I get 1 over magnitude of A must equal 1 over magnitude of B, which means that the magnitude of B must be equal to the magnitude of A. So if they have the same lengths and the dot product is not 0, so if the dot product is not 0 and the vectors have the same lengths, then the component of B onto A and A onto B should be the same. Does that make sense to you? Let's say that we have two vectors, okay? And let's do it in two-dimensional space so it's easier. And let's just say you take some vector. Here it is, okay? And now I come up with another vector that is, the dot product is not 0, so they are not perpendicular. So I cannot do it like I can't do this, okay? I can't make a right angle. So assuming I cannot make a right angle, then I'm saying that the lengths have to be the same. So let me make, I don't know how long this is. Let me make this a little more accurate. I'll make this exactly one of these pins. And then I'm going to do another pin, so somewhere around there. All right, so if you project this one onto the red one, you get some length here. But if you project the red one onto the blue one, you're going to get the same length. So these two lengths are the same. So the component of B onto A is equal to the component of A onto B. That'll happen when the original vectors' lengths are the same, so long as they weren't perpendicular. Now, what if they are perpendicular? Okay? What if they are perpendicular? Well, if they are perpendicular, right, then this side is 0 and this side is 0, top and bottom, top here and top here is 0, and then we would have equality still. The only thing we have to be concerned about is, do we have division by 0? But the problem says assume that A and B are non-zero vectors. So the length of A and the length of B can't be 0. So what we're saying now is this, that and originally we had said if the dot product isn't 0, then the lengths have to be the same. Now what we're saying is this actually doesn't matter, because if they are 0, right? If they are actually 0, then these two are equal. So we kind of have two different things. We have this. We have this. So when are those two the same? So when does the component of B onto A equal the component of A onto B? Well, if the magnitude of A equals the magnitude of B, or if A dot B equals 0, so if they're orthogonal. That's the two ways it'll happen. Now let me look at the orthogonal case. Let's say we come back in here and I draw a vector. And then I draw another vector that's orthogonal to it, which would be over here. Something like that. And notice they don't have the same lengths. Doesn't matter, because when I take this blue one and I project it down to the red one, I have to come straight down. So it's the 0 vector. And the same thing, if I project this red one down to the blue one, because it's orthogonal, it's going to be the 0 vector. So they will be equal, the components will be the same. So there's two different ways it could happen, right? It could happen if the lengths of the two vectors are the same, or it could happen if the dot product of the two vectors is 0. All right, I'll let you do part B, and that wraps it up for the homework for 10.3.